couple to the detailed session. So the first speaker is Trancanelli, right?
Hi.
From Bologna. And he tells us Wilson loops and defect RG flow in ABJM. So please.
Okay, thank you. So let me thank the organizers for inviting me. It's always nice to be back in Trieste. And okay, so I'm going to talk about two recent papers done in collaboration with people in Bicocca. Luigi Castiglioni, who's a PhD student of Silvia Penati, and then Marcia Tenser, who is sitting in the audience there. So just as a motivation, let me remind you why Wilson loops are very interesting observables to consider in any gauge theory, but also in supersymmetric gauge theories, because they have to do with lots of different things. So they have to do, of course, with supersymmetric Wilson loops. They have to do with exact results, supersymmetric localization, because they can be computed exactly. So matrix models, they can be used to test S-duality. They have to do, of course, with holography, because they have a dual interpretation in terms of minimal surfaces, bubbling geometries, D-branes, and so on in holography, allowing for precision tests of ADS-CFT, for example. In this talk, I'm going to focus mostly on this interpretation of Wilson loops as defect conformal field theories. So one-dimensional CFTs, and we are going to see this in three-dimensional, in the case of ABJM, a three-dimensional Chern-Simons matter theories, in which Wilson loops are very, very important, and they have a very rich moduli space of possible operators. So Chern-Simons theories in three dimensions, supersymmetric Chern-Simons theory in three dimensions with n larger or equal than 2, display a very large moduli space of Wilson loops, which preserve various amounts of supersymmetries of a theory, of a matter theory, of a Bach theory. So from 0 to half of the supercharges. And in this talk, I will deal with ABJM. And I'm going to show that there is an elaborate network of interpolating parametric BPS and non-BPS Wilson loops that are related by various flows. And one can regard these operators as one-dimensional defects on which non-trivial RG flows are possible, connecting superconformal theories defined by specific operators. For example, one example that we're going to see is an RG flow between a UV fixed point given by a defect CFT defined on a so-called 1/6 BPS Wilson loop. So a Wilson loop preserving 1/6 of the supercharges of a BJM, which has SU1, 1/1 group, and flowing to an infrared fixed point defined by a defect CFT on the half BPS Wilson loop. So this preserves 12 of the supercharges of the theory with SU1, 1/3. So this is very similar in spirit to what has been done in four-dimensional n equal to 4 super Mills. This has been initiated by Polchinski and Sally in 11, and then it has been studied by many people, mostly Beccaria, John Bitzaitlin, and others, in a series of papers, in which you have an interpolation between two different Wilson loops. So this is the generic Wilson loop in n equal to 4 super Mills, which is the trace of a path-order exponential of some gauge field connection plus some coupling to the scalars of the theory. I'm going to explain where this comes from later. But then, okay, so if you know Wilson loops, you notice in n equal to 4, you notice that there is an extra parameter zeta here, which is some interpolating parameter that interpolates between the ordinary non-BPS pure gauge holonomy Wilson loop when zeta is equal to 0 to the 1/2 BPS Wilson Maldacena loop when zeta is equal to 1. And there is a non-trivial RG flow between these two operators dictated by this beta function computed at leading order in the coupling of the theory. And these people showed that there is, okay, of course, there are two fixed points. At zeta equal to 0, you have a UV fixed point, which is given by the so-called ordinary, non-supersymmetric Wilson loop. which gets deformed by some marginally relevant deformation, which is this scalar coupling theta m phi m. So phi are the scalars, and theta is just some scalar coupling. And so this deformation drives the system towards the infrared fixed point given by the Wilson-Maldacena loop, the supersymmetric one. So in ABJM, the situation is much richer than just this single flow. In fact, there are many possible interpolations, including BPS and non-BPS points as in Polchinski-Sully. So in particular, I'm going to give you an idea, just a hint of schematic hint of what we did in these two papers. And so you see there are various fixed points given by various Wilson loops preserving varying amounts of both supersymmetry and asymmetry. And so in the first paper, we consider this kind of interpolations between the 1/6 BPS bosonic Wilson loops, which preserve some SU2 times SU2 asymmetry, and then flowing towards the 1/2 BPS Wilson loop preserving SU3 asymmetry along some green lines which are given by 1/24 BPS Wilson loops that we discovered in this paper. Okay, and then we are going to see that there's another half BPS operator, which is, although it differs trivially from this one, has actually a very different interpretation in terms of RG flows. And then in the second paper, we consider a more complicated situation in which we have also non-supersymmetric Wilson loops, this black points, which are connected by different parameters. So this has some set of parameters connecting them, and this has another set of parameters. But in general, in these pictures, we have bosonic deformations along the horizontal axis and fermionic deformations along the vertical axis. So in particular, these guys are mixed bosonic and fermionic things, and these are, you see how they're related heuristically. And we consider circular Wilson loops. Okay, so let me give you an overview, a brief review of Wilson loops in ABJM. So ABJM is Vn equal to 6 superconformation Simon's theory, matter theory in 3 dimensions, which is the three-dimensional cousin of n equal to 4 super-Young mills in 4 dimensions. It has 24 supercharges, SU4 are symmetry, and the field content is represented by this quiver diagram. And this is very important. So the fact that there is an underlying quiver diagram is going to be very important in order to find BPS Wilson loops in this theory. So we have 2 nodes with 2 gauge groups, A and A hat, with different ranks for ABJ, same rank for ABJM. And then you have scalars and spinors by fundamental representations and anti-fundamental representations, where this index I goes from 1 to 4. Because it is this SU4 asymmetry index. Okay, so how do we construct BPS Wilson loops in ABJM? So this is more complicated than what you do in n equal to 4 super-Young mills. So in n equal to 4 super-Young mills, the way you construct BPS Wilson loops is the following. So you take some generalized connection like this, in which you couple the operator both to the gauge field, as you would usually do, but also to the scalars of the theory. One way to understand this is to remember the 10-dimensional origin of n equal to 4 super-Young mills, in which you have n equal to 1 super-Young mills in 10 dimensions. And then you can think of doing some dimensional reduction in which 4 dimensions remain the geometric dimensions coupled to the gauge field, and then the other 6 dimensions become like an internal space dimensions coupled to the scalars. Okay, so this is one way of thinking about it. So you have a space-time contour and then some internal space contour. This in 10 dimensions, everything is going to be coupled to the 10-dimensional gauge field. But when you dimensionally reduce, you have gauge field and scalar field. So this is one way of thinking about this. So in this case, you take just supersymmetry variation of W equal to 0, then you require that the exponent is equal to 0, and then you try to solve this equation. So this is an equation for X and theta. So you can solve it and find different contours and different couplings. And okay, so one finds several solutions preserving different amounts of supercharges of the underlying theory. So for example, the most BPS examples, which are the 1/2 BPS operators are the ones in which x is the infinite straight line or is a circle. And the coupling is just a unit vector which you can take to point in any particular direction. So in particular, this coupling will break the S of 6 symmetry, R symmetry of the theory down to S of 5, right? Because you have to pick one direction. You have to couple the operator to one particular scalar. So if you try to repeat the same thing in ABJM, this doesn't quite, I mean, it works, but it's not the most general thing that you can do. So in ABJM and other three-dimensional quiver theories, this is too restrictive. In fact, the most BPS operator, the 1/2 BPS operator, is already not in this simple form. And there is a very nice, there is a way to understand it. So first of all, in 3 dimensions, the scalars have dimension 1/2. So what you couple in the operator are scalar bilinears, right? That of course can be built in the correct representation of a first node and second node. Okay, so this is in the adjoint of the first node. This is in the adjoint of the second node. And then, okay, you try to redo the same thing. Now, instead of having some theta phi, you have bilinear, so you have a matrix of scalar couplings. But if you try to do that, you don't find the half BPS Wilson loops as you were finding before, but you find only the 1/6 BPS bosonic operator. And so what you actually need to do, you need to require that the variation, so you don't require that the variation of the exponent is equal to 0, but you require that the variation of the exponent is some total derivative. And so you define, now I'm going to explain where this comes from, with this S come from, but so you have some connection, and then you require that the variation of the connection is the total derivative, so that gauge invariance of the loop guarantees BPSness of the loop, okay? And actually, it turns out that, as I was telling you before, the quiver structure of the theory is fundamental, is very, very important, so you have to exploit the quiver structure of the theory in order to build these operators, and you do that by actually discovering that this connection is not a connection, but it's a super connection. So it has, 2 diagonal blocks with these bosonic components, but also it has fermionic of diagonal entries. And then you have some super trace or a trace. I mean, there's formulations in terms of traces of super traces, but now the most modern formulation given by these people, including Marcia, in 2020, has to do with a super trace. Okay, so depending on the shape of the contour, we always consider circles, and these couplings, they may preserve various fractions of supercharges from a minimum of 0, so ordinary Wilson loops, or 1, this 124 BPS Wilson loops that I was mentioning, to a maximum of 12 supercharges, so the half BPS Wilson loop. And just some advertising, advertisements. So recently there's been lots of progress in trying to achieve a full classification of the full mapping of a modular space of BPS Wilson loops in 3-dimensional quiver theories with n larger or equal than 2. And the main idea is to start with some known operator, to deform it in this way, where Q is one of the supercharges preserved by the original operator, and with some deformation that guarantees immediately BPSness. And now depending, so the deformation has this kind of structure, and for specific forms of this G, the new operator can display supersymmetry enhancement compared to the original one. Okay, so and then we try to use this construction to really understand what is this rich zoo of operators in 3 dimensions. And if you want to have a review of things that were known until 2020 about these things, there's this roadmap paper that we wrote some time ago with lots of people. Okay, but now let's go back to Polchinski-Sully, in which I told you, okay, there was this ordinary Wilson loop in n equal to 4 supergamets, so this pure gauge holonomy without any scalar coupling that represented the UV fixed point from which we trigger the RG flow by introducing this scalar coupling. So the first question that you need to ask in ABJM, okay, so what is the ordinary non-BPS Wilson loop in ABJM? And it turns out that it's not just this guy, it's not just the scalar coupling, the gauge coupling, but you need to introduce a scalar coupling, and you do it in a way that, okay, so this guy by itself is R symmetry, preserves the full R symmetry, the full SU4 of the theory. So you need to do the same, and so you can, of course, since in 3 dimensions you can build bilinears of the scalars, you can build an SU4 invariant bilinear by contracting VI and J indices, which is something that you couldn't do in n equal to 4 supergram mills, because in n equal to 4 you had just one scalar by dimensional reasons. So you had to, you would always break R symmetry by introducing this to SO5. Now you can keep the full SU4, and now they preserve, they have the same dimensions, they preserve the same R symmetry, so they are going to mix under renormalization. So even if you don't want to include this, when you start doing computations, you're going to find that you generate a divergent graph in your way of computing Wilson loops that you cannot renormalize unless you introduce the corresponding vertex in the starting theory. Okay, so I'm going to tell you where this comes from. Okay, so for the moment, let's notice that there are 2 such ordinary Wilson loops with a plus and a minus coupling. This sign seems to be harmless, but actually is going to give lots of differences between the under RG flow between these 2 operators. Okay, but okay. So for the moment, let's remember that you have. So we discovered that the ordinary Wilson loops in ABJM, actually there are 2 of them, and they couple to the scalars in this way, not only to the gauge field. Yeah. Yeah. Sorry, I didn't say explicitly, but yeah, there are 2 nodes with alternating opposite Chern-Simons levels. So, but then there's also cyclic potential in ABJM. So it's actually you cannot just map one into the other by some field redefinition because there are really different operators. But they both preserve the same R symmetry. They don't preserve any supersymmetry, but preserve R symmetry, and they don't. Okay, so in the first paper we considered deformations that that always preserve some degree of supersymmetry, and we had 8 parameters to do that, which are these alpha and betas. So if you remember, these M's, M and eta bar are couplings to the scalars and coupling to the fermions of the theory. And now you can parameterize these couplings in terms of some parameters and define some operator which generically preserves just one supercharge of a theory. And then by selecting special values of alpha and beta, and by the way, this alpha and alpha bar, they are not complex conjugates to each other. They're just two independent, 4 independent complex parameters. And the same for betas. And okay, so for example, you can go from something which is generically 124 BPS to something which is 16 BPS fermionic. So it's something which has still some fermionic coupling. So it's still a superconnection. There are 2 of them. These operators were discovered in 2015 by these people. And then depending on how you fix the remaining parameters, you can either go to the 16 BPS, which is the simplest Wilson loops in ABJM, which was discovered by these people in 2008, or you can go to these 2 1/2 BPS operators, because I didn't tell you, but there are 2 of them that again differ just by a minus sign in front of a scalar coupling, which were discovered by us in 2009. Yeah, so this is, you can start off, as this being the most generic operator, which doesn't preserve the least amount of supersymmetries, and then by selecting specific points, you get supersymmetry enhancement. Yes. Yeah. So this is quite generic in these constructions. Yes.
And these optimum betas, these are the relevant definitions.
Yeah, so these are parameters that you are going to turn on, and we are going to have some beta function. We're going to study this. So this is the first trajectories that you can study. Then in the second paper we did something more generic, which is more in the spirit of Polchinski-Sully, which is including these non-BPS operators in black. There are various of them, and you know, you have more possible trajectories. And the idea is, okay, so for example, this is for a bosonic Wilson loop in which you have just, so this would be really the analogous of Polchinski-Sully, in which you have just the gauge field and some zeta deformation of a scalar coupling, and since now we have 4 scalars instead of just one possible scalar, you have 4 possible parameters. Of course, you could even have non-diagonal deformations, but we didn't consider them. And then you can do the same thing. So this zeta 1, zeta 2, zeta 3, zeta 4 would be like the zeta of Polchinski-Sully, and then you could have also fermionic deformations. Now, instead of having just a node in this connection, you would have a super connection with more complicated things. But anyway, you can do that, and the deformations in this case, so we call them chi. So there are deformations in these eta parameters.
So how did the horizontal allow?
So the horizontal arrows, so these are purely, so you start from the guy that has 0, 0, 0, 0 here. So this is purely bosonic. This would be this case. Now you start turning on zetas. So for example, if you turn on...
So it is not an RG flow.
Yeah, these are going to be RG flows. Yeah, these parameters are going to be governed by some RG flow, by some beta function. So there's going to be some beta function for these parameters that we're going to compute. Yeah, so this is a depiction of the RG flows, of the possible RG flows.
What is energy scale? I understand this vertical line corresponds to the energy scale, but horizontal.
No. This corresponds to the kind of deformation that you can turn on. So because since we have super connections, you have bosonic and fermionic deformations. And in this picture, we just write down bosonic deformations in the horizontal direction and fermionic deformations in the... So for example, in order to go from this guy to this guy, you need to turn on fermions. Yeah.
So this is fermionic deformation. This is bosonic.
Right. Yeah. So this would be like these zetas on the horizontal, and these chi's that I didn't write down because they are too complicated would be in this other deformation.
This horizontal arrow is the direction of modulation group 4. So you start from W minus.
Yeah. So all the arrows go from the UV to the infrared. Yeah.
How could we both are related by change of the K?
No, they are not just related by change of K. They are generally different operators. That was what I was answering. Yeah. There is no field redefinition or K redefinition that goes from one to the other because of, the operator itself, yes, but in the theory, because,
W plus.
sorry?
If I will start with UV, W plus, where it will flow infrared, W plus.
So from W plus, you can go, so this is the most stable infrared attractor is W plus 1/2.
It cannot go to W minus.
You cannot go to W minus. Okay, so how do we compute Wilson loops in this?
So this happens BPS Wilson line. So it looks like maximally stable somehow. At least on the
Yeah.
What if your loop breaks for symmetry entirely? What happens? Is it completely stable under any deformation?
Yeah. So this is stable under any deformation. So at least in all the things that we always find this to be an attractor, and yeah. So how do we compute, for example, the expectation value of these Wilson loops, or how do we do all the computations that we did? The way is to reduce this computation to an effective one-dimensional theory on the Wilson loop contour, and which is something that was introduced for QCD way back in the 80s. And the idea is the following. So, okay, forget about supersymmetric Wilson loop, just think about ordinary Wilson loops in QCD, for example. So you have a connection, which is just the gauge field. And so crucially, there is this path ordering exponential, there's the path ordering of the exponential. So when you expand the exponential, you have to order the tau parameters that you can do by introducing some step functions. Now you can reinterpret these step functions as the propagators of some auxiliary fermion field zeta, which lives on the Wilson loop contour. And then what these people did was to consider an effective one-dimensional, theory, which is given by the original theory S. So there is always an interplay between, of course, the theory living on the defect and the bulk theory. So, for example, there are vertices in the Feynman diagrams coming from the bulk, plus some action for this auxiliary fermion field zeta, which has some connection, which is precisely a Wilson loop connection. Okay. So and then, if you do the Gaussian integral, you can show that the 2-point function of zeta is the expectation value of a Wilson loop. Okay, so essentially you can compute this expectation value by computing 2-point functions in this effective theory in one dimension. Now, this was for pure gauge connections. Now, if you have these super connections with these generalized gauge connections, bosonic connections, which you have a gauge field plus the bilinears of the scalars, you need to generalize this computation, and the way to do it is that you introduce some super field, you introduce some super matrix psi, which has both fermions zeta and bosons, and you can show that the expectation value of this Wilson loop is going to be given by the 2-point function of this super matrix of auxiliary scalar and fermionic fields. And now the effective action is going to be given by this. So you have some bulk action, which is ABJM, plus some action for this auxiliary fields, which are coupled to the bulk field through the superconnection of a Wilson loop. And again, you can show that at the three-level propagators of the effective fields are just the step functions that come from the path ordering of a Wilson loop, of the exponent of a Wilson loop. So then you can do computation. So I just show them to show off Luigi and Marcia's ability of computing Feynman diagrams. So you compute corrections to the fermion propagators, and then you have counter terms. Of course, you have divergences to regulate, and the fermion vertex, the scalar vertex. So in particular, so you have one vertex that appears in this kind of computations, which is the one that I was mentioning in the beginning, that is needed in order to cancel divergences, and this is why you need this ordinary Wilson loop with extra couplings. The same thing for fermion propagators and so on. Anyway, so there are many Feynman diagrams. But now, rather than focusing on the technicalities of these Feynman diagram computations, I just want to emphasize a point, which is the fact that, okay, so of course you need to regulate things, and you do that using some DRED, is called dimensional regularization with dimensional reduction scheme, which preserves supersymmetry. But essentially, we do these computations at zero framing, so f equal to 0. So, okay, so what is framing? In pure Chern-Simons theory, so in knot theory, for example, at leading order, the only diagram that you have is the gauge field propagator between 2 points. And you can regularize this by making the contour a ribbon, okay? And of course, you can do it in many ways. And by doing this, you introduce framing. So you introduce this topological notion of how many times one side of a ribbon goes around the other side of a ribbon. And so if you do the integral, you find the Gauss linking number, which survives the removal of the regulator. So you do some point splitting of the contour, then you go back. But of course you have this topological quantity that survives. And okay, so this is pure Chern-Simons, which is a topological theory. Chern-Simons matter theory is not topological, but framing is still relevant, as we shall see. But anyway, so the important observation at this point is that our perturbative computations are done at framing 0.
What it means that this value is not satisfying. To find normalization of K in Chern-Simons theory.
Sorry? Yeah.
To do normalization consistent with Chern-Simons theory, you get shift of the K, additive shift of the coupling constant K. Doesn't matter which regularization correctly, you get finite shift of the coupling constant. It's not just a question of choice.
So in ABJM, the coupling constant doesn't renormalize or anything. Right?
But you think about Chern-Simons.
Yeah. No. This was just.
Choice.
Yeah. No, I mean, this was just an insert to tell you that in Chern-Simons this is important. I mean, in ABJM you would think that is framing.
Let's put it. If you have Chern-Simons theory,
yeah.
the normalization correctly, you get additive normalization of the coupling.
Yeah.
Now you're saying you go to ABJM, have compensation of this by Fermat, so there is no additive normalization of the coupling. Is what you're saying?
Yeah. So the coupling constant doesn't renormalize in ABJM. It's yeah. Again, this was just an insert to tell you that, okay, so you would think that framing in a non-topological theory like ABJM should somehow not play a role, but somehow it does, okay. Okay, so the final result for a Wilson loop Bev, so let's think about this generic 124 BPS operator up to second order in the coupling and in K, and in the planar limit is given by this expression. And this expression reproduces correctly all known limits for the Wilson loops which have been computed. So in particular, you remember when you select these parameters alpha and beta to special values, you go back to where 1/6 PPS fermionic, 1/6 PPS bosonic, 1/2 PPS fermionic. And okay, so this reproduces correctly everything. And okay, this depends on these parameters of a loop, which is precisely, I mean, which is an effect of having performed this computation at 0 frame. So, I mean, you do the computation just by using this dread scheme of regularizing integrals, but you are not really doing this rebonization of a Wilson loop, and then you introduce some arbitrary framing. And okay, also you need to renormalize the parameters. So if you remember, there were counter terms diagrams in these diagrams. So now let me continue with these comments about framing. So of course, ABJM, you can compute it exactly. I mean, you can localize it using supersymmetric localization, and then you can reduce the ABJM path integral, the partition function to some matrix integral where you have two nodes of the quiver, so you have two blocks of eigenvalues, and N1 and N2 again, and you have Gaussian pieces, but also you have very complicated one loop determinants that give you these structures. So this is the partition function. If you want to compute supersymmetric operators, for example, the 1/6 BPS Wilson loops, what you do, you introduce in this matrix model, you introduce some insertions. So this would be the insertions so you do these insertions inside of this partition function. And localization provides a result which is valid at framing 1 as I wrote here, f equal to 1. So at framing 1, all the operators considered here have the same expectation value. So they all collapse to a point in these plots that I wrote. And this can be proven by noticing that they just differ by Q exact terms. So they are homologically equivalent. And at framing 0, this is not true. However, the results at the two different framings, for example, at framing 0, which is what we computed using perturbation theory, and at framing 1, which is what you can compute from the matrix model by expanding at lowest order in the coupling, is some phase that we found ex post. And so this is a proposal of a framing phase which has been checked up to two loops.
Sorry, is it some experimental result?
Yeah, this is some experimental result. So, of course, it would be very, very nice to understand a computation of this framing phase independently. But so this is actually an important quantity because, okay, not this case has not been considered before, the 124, but in the 1/2 EPS case, the framing phase contains information about, for example, an observable quantity, which is the Bremsstrahlung function of a Wilson loop.
So the left-hand side is computed from localization.
Yes, at framing 1.
You computing part of it.
Yeah. So then you cook up some framing factor that compensates for the two things, and I mean, of course, again, you check it order by order in perturbation theory, but it would be very nice to have a. So this is something I'm emphasizing this to say that this is really the thing that should be understood better. So framing should be understood better. Also, I'm going to claim in holography, which is something that we don't.
So can you guess a general formula for other framing?
Yeah, okay, so for this case we didn't really try because it's complicated. But for the 1/2 EPS case, people have written some framing function, and then they check that again. So if you take the derivative of a framing function with respect to a framing, and then you put framing equal to 1 or 0, I don't remember, you get this Bremsstrahlung function. So it contains some physical quantity, important quantity. Okay, so you do renormalization. For example, you remember we had these 8 complex parameters, alpha and beta. Then you have a coupling constant of the ABJM theory that does not renormalize. So you have an 8-dimensional space of possible RG flows, and you compute these beta functions. This is at leading order in the coupling, but exactly in the parameters. And this would be the equivalent of the Polchinski-Sully beta function of the zeta deformation of a Wilson loop in n equal to 4 superunits. Okay, but of course, since you have more fixed points, more complicated interpolations, you have more beta functions. Just to have an idea, you can set some of these parameters to 0. You can then look at some space of parameters, and then you can check flows between this UV fixed point, which is the bosonic 1/6 BPS operator, and to the infrared fixed point, which is one of the 1/2 BPS operators. Then you have generic lines, which are 124 BPS, and then these particular lines, which are 1/6 BPS. I mean, just by looking at the beta functions. You can also establish a G theorem, because looking at these flows, you can check that you have these inequalities just by adding these explicit expressions. So, for example, you can check that the log of 1/6 BPS bosonic of the expectation value of a 1/6 BPS bosonic Wilson loop is always larger than the log of a 1/2 EPS operator. And so if you define some G function, which is the expectation value of actually, and then this bosonic 1/6 BPS is related to the fermionic 1/6 BPS just by taking some of the parameter to 0. So x equal to 0, y equal to 0, x equal to 1, y equal to 1, and so on. Anyway, so by looking at these inequalities and defining these G functions 1 and 2 as the expectation values of the 1/6 BPS fermionic Wilson loops with this 1 and 2, there were 2 of them, you can establish some G theorem, so some quantity which is monotonically decreasing along the flow, in the spirit of what these people did in this paper.
Is there a general argument for this theorem explained in this paper?
Yeah, there are general arguments. So, given some assumptions about your so in fact, I'm going to give you an example of a situation in which you don't respect the general argument, and then you find the opposite behavior. So you find a non-reflection positive theory, which has the wrong direction of inequality. Yes, but so you can redo this thing also for the second paper for this non-BPS trajectory. So for example, this is just bosonic deformations Okay, we cannot draw in 4 dimensions, so we draw in 3, and so you take zeta 4 equal to 0, and then you have zeta 1, zeta 2, zeta 3, and you can find the various flows between these various operators. You know, if you remember, the black ones are the ones that do not preserve supersymmetries. When they are squares, they preserve SU4 symmetry, SU3, SU2 times SU2. So you have all possible interpolations in these 3-dimensional spaces. You can do also some mixed things in which you have both bosonic and fermionic. Of course, I mean, there's a zoo of possible cases, so we try to study in the paper the ones that are interesting and some representatives. And again, so you have 3-dimensional spaces in which you select put some of the parameters equal or to 0, and then you have, for example, zeta 1 deformation, which is different from the other deformation zeta, and then you have a fermionic deformation, one of these chi's, and you have all possible, again, interpolation between these points. Essentially, this is summarized in the pictures that I gave you before, in the schematic picture that I gave you before. Good. So now we can interpret all these flows in terms of defect super conformal field theories, and in 1 dimension. And so the idea is that, okay, you have the super conformal group of ABJM, which is OSP 6/4, which once you put a line or a circle in the theory, gets broken down to the one, but preserves a 1-dimensional conformal symmetry, which is essentially, for example, for the line, you have translations along the line, you have dilatation and conformal transformation, special conformal transformation along the line. And so, for example, if you look at the 1/2 BPS and the 1/6 BPS Wilson loops, they have 1-dimensional superconformal field theories with SU1/3 or 1/1/1 superconformal group. And then you can compute correlation functions of operators in this 1-dimensional theory along the contour. So you do that with these double brackets, and the double bracket means that you insert the operator between pieces of a Wilson loop. Okay, so in a way, so these are in the adjoint, and so this is of course something like a well-defined operation, a gauge invariant object, and so on, in which you put insertions of this operator in the Wilson loop. Okay, and then there are RG flows that connect different superconformal defects seated at different fixed points. And one can compute anomalous dimensions of the parametric deformations of the theory at the UV fixed point. So, for example, let's consider this particular 2-point functions of psi bar. You can compute it, and then you can extract from this some anomalous dimension, which you find to be negative, which confirms the weakly relevant nature of this deformation that is something that you turn on at the UV fixed point and triggers this RG flow away from it. So in general, when you turn on some deformation operator, but let's call it D hat, which has some coupling whose beta function is beta I, so this is the beta function of a corresponding coupling associated to this deformation operator, then you turn on a defect stress tensor, TD, and you can take derivatives with respect to the renormalization scale of this quantity, and you can extract from this definition a matrix of anomalous dimensions of the deformation operators. And then, okay, so this delta is the total dimension, which has some anomalous part and some classical part, and you can compute this matrix of anomalous dimensions. For example, think about bosonic deformations in which you have all these zeta parameters equal to 1 zeta, and then so the deformation parameter would be Ci C bar I, which is what you turn on, and okay, you have some beta function of the corresponding zeta. You can compute the resulting matrix of anomalous dimensions around the zeta equal to 0 fixed point, and you find that this is, this is a 4x4 matrix, which has a diagonal 4x4 matrix, so there's an identity 4x4 here. So this is negative, showing that around the non-BPS operator W minus, the deformation is indeed weakly relevant. If you redo the same computation around z equal to 1, which corresponds to the attractor W plus, then this is positive and the associated deformation is irrelevant, marginally irrelevant. Again, you can test the validity of a G theorem in this setup in which you have more general operators, including the non-BPS ones. And okay, so you can define. So remember, before G was defined as. Sorry, I'm missing a log here. It was the log of the expectation value of a Wilson loop. So you can define a quantity which is related to the log of the expectation value of a Wilson loop, which is this defect entropy, which corresponds to the log at the fixed points, log of a Wilson loop at the fixed points, and then you can show that this quantity is given by the 2-point function of the defect stress tensor on the contour. So, for example, think about the flow, this horizontal flow between W minus and W plus that I was showing in this schematic picture before. So you can compute this quantity for the flow between these two ordinary Wilson loops, and so now the defect stress tensor is just the Ci, C bar I, so the operator that you turn on to trigger the flow. You get this quantity, which is negative. So from this, you can show that the G theorem holds. So you have a quantity which is monotonically decreasing along the flow, which is given by the log of this object.
And these G's for you are always positive, I guess. Is that right?
Yeah.
So in 0, it's like topological line, I guess, right?
Which 0 is?
I mean, G hits 0, then it's some kind of group like topological line. So I guess there'll be no flow associated.
Yeah, maybe. Yeah. Because the Wilson loop is always fine. So the Wilson loop has a finite expectation value. So so this was what I showed you before was just this one, going from W minus to W plus. Now let's consider, for example, what happens if you turn on fermionic deformations. For example, along these two vertical lines here. So things are more involved, and in fact there are, as is clear from the picture, there are two half EPS operators that they differ just by a sign, apparently harmless sign in front of a coupling. So one has some matrix M, the other one has some matrix minus M of scalar couplings and some other minuses in other places. But okay, classically they preserve the same supersymmetry, they preserve the same asymmetry, so they are the same. Except that when you compute this defect entropy for these two operators, you find that which again differ just by a sign that we call L. So in one case, you get a negative answer, and in the other case, you get a positive answer. So in one case, which is the case associated to this flow here, you get that the G theorem holds. In the other case, which is this flow here, you get that the G theorem does not hold. Of course, I mean, we understand this technically. We understand it from perturbation theory because there is a crucial minus sign difference in the 2-point function of the defect stress tensor. But maybe this can be interpreted by the fact that, okay, so, but by the fact that the one-dimensional theory defined on this defect is non-reflection positive, which was one of the assumptions for the validity of the G theorem. And in fact, this is something that has been found independently in another setting by these people here. So also they found this, that there are these two operators, again, in a slightly different setting, but one of them gives rise to a reflection positive theory, and the other one does not.
So you said you have a flow from this W1.5 minus the black triangle.
Yeah.
So the starting point is unitary. I mean, reflection positive.
No, we are claiming it is not.
And
So
the end point, the black triangle.
the black. So we didn't study. No, okay. So we didn't study. Okay, so here, yeah, here it is unitary because here you have this flow where everything works fine. Yes. Although we haven't really checked independently, but it should be fine. It should be unitary. Anyway, so I'm concluding, I think. No, okay, I still have a little bit of time. So we have studied RG flows connecting a large set of fixed points represented by BPS and non-BPS Wilson loop operators in ABJM theory. Some of these flows are associated to at least one supercharge, so preserve at least one supercharge, so there are 124 BPS Wilson loops, something that can be dubbed as a rich flow, so there are flows that preserve at least one supercharge, while others are non-BPS, the ones from the second paper. And we have also computed the VEV of the generic 124 BPS Wilson loops to second order and checked it against known limits. So again, our computations are at framing 0, which is what one is able to do. Unfortunately, it is beyond current technology to be able to compute. So the problem is when you have fermionic integrals. So integrals coming from fermionic Feynman diagrams. So at framing 1, which is what is being evaluated by localization. So it would be nice to find I mean, this is in general, not only for our paper, but for hundreds of other papers that have been done in perturbation theory in ABJM. So it would be nice to have a direct way to compute things in perturbation theory at framing 1. So maybe you have to add local counter terms to your action that, you know, take into account the possibility of doing some point splitting which contains some framing, but you can go around the original contour. But again, so this is a difficult open problem. And a related problem is to understand the holographic dual of all this picture. Because again, okay, let me remind you what is the holographic dual of a Wilson loop in a DSCFT. So if you have a contour C, at the boundary, you have some macroscopic F1 string which extends in the bulk and lands along the contour. Okay, so this is going to give you some surface. You have to minimize the surface, and the minimal area of the surface is going to give you the VEV of a Wilson loop at strong coupling. So this is for what concerns the ADS part. And then there is the internal space part, and the string is going to do something in the internal space part. Depends on what kind of operator you consider. For example, in n equal to 4 super Mills, the half EPS operator, which if you remember had a theta which was 1, 0, 0, 0, 0. So it was just pointing, it was a coupling to one scalar. So this is an operator that sits at the north pole of DS5, for example. If you have more complicated operators, they can move around the internal space. Also in ABJM, the 1/2 EPS operator is the one that sits at a fixed point of CP3. But in more general case, we don't know. And in fact, even for very simple operators, like the 1/6 BPS bosonic loop, we don't really understand the string picture. So while these things are quite well understood in n equal to 4 super Mills, in ABJM is much more complicated. And so the dual string of this simple operator is not known. And as a consequence, there are many interesting related questions. So in particular, okay, since framing is something that I can do in gauge theory, in the gauge theory, for example, the matrix model gives me a result at framing 1. How do I implement framing in holography? So what is the correction that I have to do to this string computation in holography? So for example, how can I do a string computation at framing 0? And also, what is the dual of the ordinary Wilson loops in ABJM? So it should be a string with only Neumann boundary conditions. So of course, because I mean, if you put it at a point, you have some Dirichlet boundary conditions, which is what you have, for example, for the half EPS string in ADS5 times S5, in which you have Dirichlet boundary condition on the S5. But now, if you want to preserve a full R-symmetry group, somehow you have to delocalize completely the string in the internal space by imposing Neumann boundary condition, and technically it's not clear how to do it in CP3. But then there is another question, right? Because we had two ordinary Wilson loops. How does the string knows between the two of them? Because they have completely different behaviors under the RG flow. One we saw is an attractor. The other one is repulsive. So I mean, we know. So one possibility, I mean, we know that for the two half EPS Wilson loops, we know that one is described by an M2 brane on ADS4 times S7 mod ZK, but and the other one is described by an anti-M2 brane. But okay, so this is something which is more or less understood. But how does this reflection? How does this different M2 brane, anti-M2 brane reflects on the opposite behavior under the RG flow? And of course, this has, I mean, it could be very relevant, this discussion of interpolating boundary conditions in ADS2 in these papers. This is something which is, for me, is very interesting. But again, the string theory dual of ABJM Wilson loops is something complicated. Another thing which is, I think, could be cute, is to think about, so we have all these multidimensional RG flow spaces. And there is a nice paper, or a couple of papers by Gukov a few years ago, in which he studies RG flows as dynamical systems. And the idea is to use some topology to extract information. So for example, so imagine that you have some RG flow space, and you don't know anything about what happens in the interior of this volume, but you only know you know what is the direction of the RG trajectories on the boundary of this volume, on the surface. And then, for example, you can divide this boundary into regions in which the flows are outgoing and regions in which they are ingoing, again, without knowing anything. And then you can compute some index for these surfaces, and this should give you information about, for example, how many fixed points are inside of this region. So from very limited information, you can extract a lot by using these topological methods. And okay, since we have an example of a multidimensional RG flow space, could be maybe interesting to test this proposal, which is something we haven't done, but could be doable. To for example, compute Visconti indices for our spaces and to check that actually give you the right answer. They give you, okay, they detect that inside of this volume there is an attractive fixed point or so on. Okay, so this is what I wanted to say. Thank you.
Thank you very much for a nice talk. Any questions, comments?
Just to understand better this issue with framing. I'm a bit confused because that was already the beginning. Because well developed technical setup to continue to.
In which case?
ABJM theory.
In ABJM, yeah.
You start presenting some two-bit calculation with the beta function, you do some regularization, dimensional reduction, etc. As a way to reduce regularization, going away from 3 dimensions, 3 minus epsilon.
Well, or 1 minus epsilon. Yeah, okay. Yeah. There is a 3-dimensional part for yeah, okay.
Then this what you call framing. It's well-defined integral. There is no ambiguity in this integral.
No, but okay, maybe for the gauge field, right? But then there are all other coupling to the other fields. The Wilson loop has all other couplings, right?
Let's put it this way. As you introduce regularization and say with regularize, there is no issue whatsoever about any ambiguity.
Right.
And then you get something which is well defined. Or there is some issue with regularization. So my question is, the fact that discussing different values of framing, which option realize? Is the series
So-
properly regularized?
Yeah, I think what I'm doing is alternative to framing regularization. So it would be framing equal to 0.
But what does it mean physically? If you have a theory which is well defined and you regularize a certain way, there is no ambiguity left. You define the theory, and theory doesn't allow any additional parameters to be like framing, whatever. Because what is understood from the talk, you have additional hidden degrees of freedom parameters which call framing, depending on which the theory will have different. My question is, what definition of the theory corresponding to given value of the framing parameter?
Yeah, I think this is what is not known, right? Because so if you have just ABJM, I mean, if you have just pure Chern-Simons, you have this Gauss linking number that I showed, and then it comes out automatically, right?
Yeah, but then doing calculation, you have to introduce regularization. Anyway, independently of whether you Chern-Simons or not Chern-Simons, once you talk about beta function, you have some regularization introduced.
Yes.
At the moment you introduce regularization,
And
it's
essentially,
well defined.
yeah, but I didn't introduce any framing, so
No, but framing is regularization. When
Yeah.
I'm saying that I introduced dimensional regularization to subgrid, and after this, there is no issue about any other regularization.
Right.
So
Okay.
therefore, framing should come automatically as a consequence of choosing particular regularization. So therefore, what I don't understand is the things like what you're trying, my understanding, that depending on how you introduce regularization, get different physics. You're saying framing different 0, calculation, framing equal to 1, localization, so they have different expressions. Therefore, I don't understand what does it mean physically. You're talking about
Yeah, so I think physically is this framing factor, yes. So, okay. The way we do it is just essentially alternative to introducing framing, and then you have an expression that you interpret to be at framing 0, that if you want to compare with framing whatever, you need to cook up a framing phase that is not just cooked up because, I mean, it contains physical information because, for example, it contains information about the Bremse-Strahlung function, which is a physical observable, right? That not satisfactory part of this thing is that we don't know a way to compute this framing function from first principles, so independently.
Can't you do point splitting regularization?
There's no very dangerous issue, especially given gauge invariant sensitivity.
Yeah, so I think this is very complicated to do this, especially when you have fermionic integrals. So integrals coming from fermionic diagrams. I think so. Marco Bianchi is the guy who has taught the most about these things, and I think I mean, yes, and I don't know. It's an open problem, really. So.
Because in standard Chern-Simons it works. But,
Yeah, but here you have all these other matter fields, and it's not just. Yeah, it is more complicated because, especially the problem comes from fermions. Yeah.
When you say it works in Chern-Simons, it's also a very delicate question. What do you mean it works? It works, but it will give you fine thermalization of K. Let's say,
but I mean, this is a different issue. The point is that you have a Wilson loop, and then you have self-interaction on the gauge field on the Wilson loop. And then what you have to do is to substitute with a ribbon, essentially. And then the framing is how much this ribbon is twisted.
Yeah.
This is the physical meaning.
Yeah.
So if you do point splitting regularization, you can control this in ordinary Chern-Simons. But what?
Yeah. So it is not known how to do it.
When you add the
Yeah.
fermionic
Yeah.
freedom, it looks like
And well, I think. Yeah.
Is it true that it worked the way in Chern-Simons because it was topological, and but if you consider ABJMs no more topological, and we need some less regularization.
But as I was saying, if you go with this point splitting, at the moment you go to dimension, introduce dimensional regularization, you go away from C dimension. You go on propagator, gauge propagator. It gets soft and short distance, so there's no issue of regularization. It will be regularized by dimensional regularization automatically. Therefore, at the moment, as I was saying, you introduce dimensional regularization in the series, there's no ambiguity left. Everything should come out automatically.
Yeah. So.
So it should be. This is what I understand. It seems like the way how you regularize the series, you're getting different physical answers.
But what is the meaning of dimensional regularization in something like Chern-Simons, which is defined only in 3 dimensions?
Well, yeah, it's well defined. You keep the epsilon tensor as the epsilon, so you at some point, so something gets an epsilon, some things don't get an epsilon. Is this dread?
I was just curious. So, I mean, I those fixed points that you wrote down, they included some parameters. So should I interpret those as exactly marginal? That they're exactly marginal deformations as well?
Which ones?
So I remember you had some slides where you left some alphas and betas, but maybe even earlier. Maybe you had some slide where you showed the fixed various fixed. Yeah, maybe. Sorry.
Maybe this one.
So here, for example, this W124, it has alpha and alpha bar. So are those exactly marginal deformations? This W124?
No, because again, all have beta functions which are non-zero. Yeah.
I see. So even if you break some R symmetry, you don't have a choice of which direction in the R symmetry space, like some trivial marginal deformation in that sense.
No, so sorry. Say again. Now is.
So like here itself has some R symmetry, and then the
Yeah.
line may break some of that R symmetry.
Yes.
And then you may have a choice of which direction, sort of on the manifold that describes the R symmetry you're pointing. So this would be some kind of like maybe trivial marginal direction.
Yeah, so for example, here you break from SU3 to SU2 times SU2. So you do break, so the triangles are SU3 and circles are SU2 times SU2. So you do break R symmetry.
But you don't have like a choice somehow. So you break from SU3 to SU2.
Yeah. So for example, along these ones, yes.
So do you have like a marginal deformation that describes the setting of SU2 inside of SU3, for example? Trivial marginal deformation. I just imagine that there's a family of lines.
Yeah, so for the parameters that we considered, no. But I mean, it's not we didn't consider most general possible. For example, we always kept diagonal bosonic deformations, and okay, so this is.
Oh. Does Bukov care about unitarity, or maybe because it's topological, it doesn't matter? It looks very general, maybe it doesn't matter.
Yeah, it does. I don't think it matters. I think it's really some black box that some black box. You just have information about what happens here, and yeah.
So, other questions? No. So if not, let's thank Diego again.